All right, today we're stepping into the chemist's kitchen. We're going to learn the most fundamental language they use, their secret recipe book, if you will. We're going to master molarity, the system that helps scientists get their mixtures absolutely perfect, every single time.
I mean, really think about it. Imagine a recipe that just said, add some sugar to some water. How much sugar? How much water? Is it for a frosting? Or are we making simple syrup for a cocktail? You'd be totally lost, right? Well, that kind of vagueness is a huge problem in science, and the stakes are way, way higher than a bad cake.
You know, in a lab or a factory or especially a pharmacy, a little and a lot just won't cut it. An imprecise mixture could mean a failed experiment, a bad batch of product, or even a seriously dangerous chemical reaction. You just can't eyeball this stuff. This is exactly why we need a universal standard, a single, clear, mathematical way to talk about the concentration of a solution that anyone anywhere in the world can understand and replicate perfectly. And that standard has a name. Molarity is the hero of our story today. It's the internationally agreed-upon method for defining how strong a solution is. It completely gets rid of the guesswork and replaces it with cold, hard numbers. It is the chemist's recipe for precision. So here's the official textbook definition. But don't let it scare you. Let's break it down. A solute is just the stuff you're dissolving, like salt is the solute when you dissolve it in water. A mole is just a specific number of atoms or molecules, kind of like how a dozen means 12. And a cubic decimeter, that's just a fancy way of saying 1 liter. So to put it really simply, molarity just tells you how much of your stuff is packed into a 1-liter container of your mixture. It's a ratio of stuff to space. And that's so powerful because chemical reactions depend on the number of particles that are bumping into each other, not just how much they weigh. And moles give us that exact count. So how do we actually calculate it? Well, to put molarity into action, we need to open up the chemist's toolkit and look at its master formula. Here are the 3 key players. We've got M for molarity, that's what we're trying to measure. Then there's N for the number of moles, that's the amount of our solute. And finally, V's for the volume of the whole solution, always measured in cubic decimeters or liters.
And this is the chemist's little secret weapon, the magic triangle. It's such a simple way to remember how the formula works. Whatever you want to find, just cover it with your finger. Need to find molarity? Okay, cover the M. What's left? N divided by V's. Need to find the moles? Cover N. Now it's M times V's. It makes rearranging the equation totally foolproof.
Okay, let's put this thing to work. In this problem, we need to find the number of moles, N. So we look at our triangle, cover up N, and we see its molarity times volume. Our molarity is 2.0. The volume is 500 cubic centimeters. But wait, we have to use cubic decimeters or liters. So 500 cubic centimeters is 0.5 cubic decimeters. Now we just multiply. 2.0 times 0.5. And that gives us our answer. Exactly 1.0 mole. Simple as that. All right, now for another super essential skill. A lot of times in a lab, you'll start with a really concentrated stock solution, and you need to water it down to a very specific, weaker concentration. This is called dilution, and molarity is what makes it incredibly precise. Now, the key principle here, the one thing you really got to get, is this. When you dilute something, all you're doing is adding more solvent, like water. You're not actually changing the amount of the stuff, the solute that's dissolved in there. That number of moles stays exactly the same from start to finish. And that simple fact leads us to this beautiful little equation. Since the moles before you start, which is M1 times V1, are equal to the moles after you're done, M2 times V2, the formula is just M1 V1 equals M2 V2. It's a perfect balancing act. If you know any 3 of those numbers, you can always find the 4th. Okay, this is all great for a chemistry lab, but why does it matter out here in the real world? Well, as it turns out, molarity shows up in our everyday lives in some really, really important ways. Molarity is actually everywhere. It's what's used to define the strength of that rubbing alcohol you have in your bathroom, and it plays a critical, life-saving role in industry, like making sure dangerous chemicals are handled correctly when they're being trucked down our highways. Take a look at this number, 57,000 kilograms. That's how much concentrated hydrochloric acid a single tanker truck can be carrying. That's a massive amount of incredibly dangerous stuff. And for a substance that dangerous,
First responders and factory workers have to know its exact concentration, its molarity, to handle it safely. That molarity value is what determines the official hazard warning label that goes on the side of that tank. If you get that calculation wrong, the consequences could be catastrophic. This is where precision is literally a matter of life and death.
So as you can see, molarity is so much more than just some formula in a textbook. It's a universal language. It's the tool that allows for safety, for experiments to be repeated, and for all the innovation that drives modern science and industry forward. It's the recipe for a predictable and safer world.
You know, from your morning coffee to the chlorine levels in a swimming pool, precision really matters everywhere. So I'll leave you with this. What's one mixture in your everyday life that you wish could be perfectly measured every single time? Thanks for tuning in.